gravitational force stuff and just reinforce a lot of stuff from those early parts of chapter 5. John, doing all right?
So we were in Cisco as well.
Yeah, no, it's all good. Got any TV shows or anything you recommend to everybody? Anything you're watching right now?
I just finished watching Kingdom. It's pretty good.
Nice. Is that kind of like a fantasy sort of thing?
No, it's like a horror kind of movie.
Huh.
Yeah.
All right, I'll check it out. Okay, so again, you might need to refresh your canvas, but you should see the usual thing that I post, which is the Science2F tasks for Unit 4, Lesson 9. That's today, Friday. The first thing is we have a do now. This one is not graded. It'll just take you to a Google form. And there's, I think, 4 questions to answer. It's based on the activities we did in the previous lesson. So I'll time us for 3 minutes and just watch as people submit answers. I'm listening though, so just remember to mute yourself, but come back on in if you got a question or anything like that. So 3 minutes and then we'll check in again. So I just want to see how you were all feeling about these activities and what you took from them in our previous class. And so just to kind of, your discussion posts about these were also looking good. But for the first question, think back to the activity. Why did the water flow out of the hole in the bottom of the cup? Very good that all of you understand that the water is pulled down by Earth's gravity towards the center of the Earth, and the cup you were holding in place. And then when we remove that factor, when we're not holding the cup in place anymore, very good. The next question was, why did the water not flow out of the hole you made when you dropped the entire structure? And that's because the water and the cup are falling together at that point, right? Gravity is acting equally on all of those things. Looks like one person went with there's no difference. Water actually did flow downward. So it's possible that maybe you did see a little bit of water come out of the hole, but that was purely just more of a circumstantial thing, right? Gravity is acting on that falling body together. Then doing the objects, very good. Looks like most of you understood that the paper is lighter, right? It has less mass and therefore air resistance has a bigger impact on it. And that's why it fell a little more slowly, even though gravitational force on those 2 objects was equal. A lot of people said here paper had a lower mass, therefore actually experienced much less gravitational force. So this is what is, in my opinion, is a tricky thing to wrap your minds around. That even though, yes, the paper had less mass, technically the gravitational force works out to be roughly equal in terms of the forces they're experiencing. Again, something I'm still trying to wrap my mind around too, but it fell slower because of the air resistance was slowing it down. That was the big impact. But then when you're falling together, the book is essentially drafting for the paper, right? It gets rid of that air resistance, and so it falls together. And this makes me think of a couple examples. The classic one is, I don't know if anyone's ever watched any like bicycle races or like the Tour de France or anything like that. But when you watch bicyclists racing, they do a funny thing where they all get in a perfect line, like literally wheel to wheel. And does anyone know, even though it's a race, does anyone know what position they often trade off? Yeah, it's really goofy to watch, but like they trade off being in first place, right? Like you'll see the guy in the lead will suddenly drop back and let somebody else be in the front. Does anyone know why? What's the person in the front doing?
They're breaking the wind.
Yeah, so and that's what they call drafting. And that's the same thing that's happening here with this textbook, right? The textbook was drafting for the piece of paper, so then they fell together. And, you know, bicyclists are obsessed with how much energy they use. So they've literally like calculated and studied how much extra work it is. And it's pretty significant that the person who's drafting in front, who's breaking that wind, as you said, for all the other riders, has to put in a lot more energy. And so that's why you'll see they never spend more than about a minute, I think, being in the lead. And so that's why, you know, it's more at the end of the race where they all break apart and try to go for the finish line. But, you know, kind of cool thing to think about that has applications even in, you know, athletics, right? Racing. So, all right. Our 2 main tasks today are to watch some Edpuzzle videos about gravitational force, and then we're going to do another activity relating to those a little bit. But the videos are getting kind of a big picture thing. So this is my first time using Edpuzzle, but my previous classes, things went pretty smoothly. So the links are right here. The first video is about 8 minutes, which way is down? And there's a couple questions that you need to answer. The second video is only about 30 seconds long, and it's about the physics of bottle flipping, which we'll discuss a little bit more. Just to see, though, how many of you have used Edpuzzle before, like in other classes, homework, whatever? Cool. All right, most of you should know how it works. Questions will pop up, you answer them, you move on. This isn't graded. Do Now wasn't graded either, but I will collect responses and we'll kind of look over those as we get going. So I'll give you about 20 minutes to work on this, and I'll follow your progress. If you want, you can leave the room if you want, and then just come back in once you're done, or feel free to turn off your camera and mute yourself. But let's say 20 minutes from now would roughly be about 12:45. So let's plan to be back here in the room at around 12:45. And I'll still be here listening. If you've got any questions or something isn't working, just let me know. So, all right, 20 minutes, go for it. All right, so let's take a look at your responses and just quickly chat through these. First video I'll go through is the 8-minute one from Vsauce. Let's see how we did. So all of you got that first one right about the difference between mass and weight, and that's a really important distinction in physics, and it's one that confuses me as well. But the point is that depending on your location, can your mass change? Like, do you have a different mass on the moon versus here on Earth?
No.
No.
You don't, right? Your mass could change very suddenly, though, if what happened to you. I know it's kind of gruesome, but how could you change your mass? Yeah, if you got your arm blown off or if you got sliced in half, technically your mass would have changed. But mass is just the amount of matter that you are made up of, right? Weight is dependent on gravity, right? We have a certain weight here on Earth. You would have a different weight on the moon, a different weight in space, a different weight on Mars. So that's the key distinction. There are two different things. And so this brings this next question, which is kind of silly, but we describe astronauts as being weightless, not massless. Did anyone get this? What have you done to your astronaut if they have become massless?
They wouldn't exist.
Yeah, you have made them disappear. They would not be there. Because again, mass is how much matter you're made of. If you're massless, you have no matter. And so, even that term weightless, though, is sort of misleading. Because again, I want to reinforce this, even when in space, are astronauts actually experiencing zero gravity?
No.
They aren't. It's just a weakened form of it, right? And it's actually how we perceive it, which is another thing that he gets at in this video. So what does Michael mean by weight is mutual? And again, this is the kind of thing that just really blows my mind, that forces act in two different ways. And so, yeah, if you weigh 200 pounds on the Earth, then the Earth weighs 200 pounds on you. All of you right now are probably sitting in a chair. And so, again, I know it's weird to think, but you are weighing on the chair. But what else is true?
Chair's weighing on you, if that makes sense.
Chair's weighing on you, exactly. And so it's sort of a perspective thing, right? It's about, I guess, what you're looking at or what's experiencing the weight. And again, that's one of those things that really kind of confused me in chemistry, but you've always got to draw two arrows going in opposite directions. And it's not like it means things float around. It just means you've got these two forces. It depends on your perspective. What would happen to the ISS, the International Space Station, which is currently in orbit, if it were to suddenly stop moving? What if it were to stop, actually have no tangential velocity anymore? Anyone know?
It would fall.
Come crashing to Earth.
Yeah, it would come crashing down to the Earth, just like what? Again, what did Newton observe falling at first?
An
apple.
Yeah, it would fall just like an apple from the tree, right? That would be a little more disastrous because it would also have to go through the atmosphere, but it's the same thing, right? Gravity is acting on all of those the same way. It's just that the ISS is moving very, very fast sideways, and that's what keeps it in space, right? It does multiple rotations around the Earth, even in, I think, a matter of hours. What does it mean that astronauts have no apparent weight? Very good. Looks like most of you got that it means all of those are true, right? Which must be a really weird experience, but they're not worried about tripping on anything. They're never going to feel sore, right? Their butt will never feel sore no matter how long they sit somewhere or if they're on a bike seat. When they go to bed, they're not feeling the sheets on top of them, which to me must be such a weird experience. And I strongly encourage you, if you haven't done this, hop on YouTube and check out. There's really cool videos about like life in space and living in space and what it's like for astronauts. Does anyone know when they go to bed, what do they have to do when they go to sleep?
Strap themselves in.
Yeah, it's funny. They put on all these seat belts. You have to put like an upper chest harness on and then your legs as well, because otherwise they don't want to end up floating off somewhere while they're asleep and wake up in a different part of the space station. And again, it must be so weird getting into a sleeping bag and zipping it up and not feeling that like the weight of it on you, like you're just kind of floating inside of it. Anyway, it must be really weird. So what does Michael mean when he says that if you weighed yourself in a vacuum, you would weigh about this much more? And when he's referring to an apple, which has 1 Newton of weight force. What is a vacuum? Like, if you were to weigh yourself in a vacuum, what does he mean by that?
Like there's no air.
Yeah, so you've taken out everything, right? Yeah, you're just in empty space. And so it turns out air actually buoys us a little bit. It makes you lighter. And so if you were to remove that, you would be heavier by the weight of an apple. It would be like somebody handed you an apple and you were holding it. That's how much heavier, which doesn't seem that significant, but it's kind of interesting to think about. And the big takeaway from this video and the title of the video is which way is down. And so why is down always changing? What were some of the things he talks about?
There's different center of masses in like many different areas. So like your gravitational like attraction to different things is like different all the time, like especially like the moon. So technically down changes.
Yeah. He talks about the center of mass of the Earth, but what have we learned is true about the center of the Earth?
It's lava.
It's moving.
Yeah, it's moving, it's molten. And so all that metal might be in one location, but then it moves to another, and that really contributes to gravity. So it's kind of an eye-opening thing to me, because everyone talks about how physics is like the purest science and it's the most accurate thing you can study. And yet it's cool to see that they still also have to make assumptions, right? Like we assume that the center of gravity in a planet is the center of the planet, when in reality, it's not actually true. It's constantly changing. And like Hank mentioned too, the moon position, right, whether the moon's above us or on the opposite side of the planet as you, can also make a difference. Now, do we perceive these differences though? Like, do you notice like, oh, down just shifted a bit?
No.
Not really, right? They're pretty minuscule. Who knows? There might be living things that are sensitive to that kind of thing, but doesn't make a big difference. The last video was all about this little trick that was everyone I felt was obsessed with. I'm sure all of you got into bottle flipping. Anyone get particularly good at it, or feel like they still are? Bear Scherner in my previous class was saying that he got 22 in a row once. Anyway, I thought that was impressive. I don't know if anyone's tried how long you can do that. But just to get to the physics of this, there was only the one question. It's actually some complicated physics going on here, and I'm hoping we'll explore it later. But the point is the liquid. What do you notice about where the liquid is in the bottle, even when it gets flipped upside down initially and then lands?
At the bottom.
Yeah, still stays in the bottom. And so it's kind of cool that the force you apply while you're flipping this bottle is enough to overcome the gravitational force of Earth, right? It shows you, again, the small values you're actually dealing with there. And then the water actually does slosh back just a little bit. And apparently that's the key to landing it, that you want that sort of slosh, because then that's why the bottle suddenly just lands very violently. It's because of the weight and the spin is changing. So again, something we might explore in a little more detail later. All right. Any other questions or comments on that? I skipped step 2, which was to check in with the homework, which I know we would normally do in class, so I want to keep up that same thing. The chapter 5 homework from the reading, just to give people an opportunity. Again, you had to answer questions 1, 3, 5, and 7. Were there any questions on this? Anything you left blank? Anything you needed help with, or that wasn't clear? All right, seems like we're feeling good. I'll check all of that later. I now want to do an activity, hopefully get you up and away from your computer. I've got a video kind of showing what I want you to do. So we'll watch the video, check in to make sure you feel like you're good. And then again, I'll probably give you about 15 or 20 minutes to work on this. So I'll actually just play the video through Zoom, because that seems to work well. So is everyone seeing the image of me in my kitchen? Yep. All right, here we go.
Hi, Science 2 kiddos. 2 activities that I want to do today, again involving the water. The first is to get another
How's the audio? Everyone hearing it? All right.
Container, like again, a paper cup or a recycled plastic jar, something like that. Do not use anything that's glass or porcelain, because we're going to be moving these around a little bit, and I don't want anything to break if you drop it. First thing I want you to do is just fill up a container with water, maybe about halfway. And then just a simple demonstration of gravity. obviously if I take this cup of water and I turn it upside down, water pours out. No surprises there, right? We know the gravitational force is pulling the water down towards the center of the Earth. But what if I told you that there is a way that you could flip this container upside down and keep the water inside of it without having to put a lid on or anything like that? That's what I want to explore today. So again, let's fill the container up probably about 3/4 of the way. I'd say maybe just below 3/4 is how much you want to fill your container up. And I think you can predict what we're going to do, but we're going to try to use centripetal force. It's the same concept behind why the moon doesn't fall back down to the Earth, right? That it has this tangential velocity that just keeps it falling all the way around the planet. This is a little bit different, but we're going to sort of use another force to keep the water in the bottle. Now, this is going to be a little bit of a delicate procedure. I would like you to try this. But please, again, do this in a clear space where you can, where you have space you're not going to hit anything, maybe somewhere where you're not afraid to spill a little bit of water. And again, please use a container that isn't going to break if you accidentally drop it. But what you want to do is get a good grip on the container. You want to keep your arms straight, and you want to just do a full rotation all the way around. Again, make sure nothing's behind you. Make sure it's good. And you'll notice the water did not spill at all. Now, I had to put a little bit of strength into it, right? You've got to go fast. If you go slow, the water is definitely going to spill. But if you go fast enough, I generate enough force to keep the water in the bottom of the container. Now, here's the thing. If I tried to do that in a smaller rotation, for example, like right here, it's not going to work nearly as well. Right? If I try to flip it just like this, then it's not doing all that well, right? I could try it like that, but that small rotation doesn't give us enough force. And so the best thing to do is to actually empty the bottle out, which mine was already a little bit empty. But if you have less water in there, that's less mass. And remember, mass is directly proportional to the gravitational force. So it's going to take a lot less force for me to counteract the force of gravity coming from the Earth. And so now I should be able to just flip this cup now without even having to use my shoulder as a rotation point, and I can still keep the water inside the container. So again, I'd like you to try that. This is what I'd like you to try to document or film. And as I was preparing for this, I was reminded of some popular videos that came out a couple of years ago where everyone was obsessed with flipping bottles. And this does relate a little bit to that in terms of how the liquid behaves. There's a lot more going on with bottle flipping, and hopefully it's stuff that we'll get into more as we get deeper into physics with rotation and center of gravity and things like that. But it's sort of similar that if you'll notice that the water stays on the bottom of the container even as we flip it up. So what I'd like you to do is just to demonstrate that you did these activities, use your phone to take a little selfie video of the last two things. So I want you to take a video of you rotating your container in a small rotation. So you can just hold your phone out like that, have your container here, and just do the little small rotation there, showing me that you're keeping the water inside of it. And then you can have one attempt at a bottle flip, whether you make it or not. Only record one of them, and that's it. Then you just need to upload that video. It shouldn't be more than maybe a minute at most. Upload that video to Flipgrid through the link that is in the tasks on Canvas. And as always, then make sure that you have cleaned up your space. If you spill any water, dry it up, throw away the container if you used a recycled container, right? Make sure you're keeping your space clean.
All right, any questions on that and what you're doing? So again, the two things are the small rotation and the bottle flip. You have one chance. Can we all appreciate that I landed it on my try in that video? I shot that video like 20 times. That was the one time I made it. So no, I'm kidding. That would have been a long night. So, and again, the Flipgrid is already set up. And as far as I know, it's pretty straightforward to upload. Instead of hitting the record button on Flipgrid, you just hit the 3 dots on the other side and it lets you upload a video. So that's what you need to do. And so I'll give you about 15 minutes to work on that. So let's plan to come back into the room here at 1:15. And again, I'll be here listening if you have any questions. Go for it. How'd that go for everybody?
It was good.
You should check out each other's videos. There's some pretty good ones being posted right now.
I landed a milk bottle flip.
I saw that. Yep. A milk jug, a 1 gallon.
Yeah, a gallon jug.
Yep. Yeah, you should go check out some of those just to show you a couple. Yeah, so here's Hank landing his milk jug. Pretty good. Kenson also had an impressive little like sink side landing.
Oh my goodness, water came out. Oh yes sir. All right, water bottle flip. Nice flip. Real quick. Oh, that didn't even land. Yes,
Oh,
sir.
there you go, right on the edge. But my personal favorite for, in my opinion, the most vicious one was John by far.
All right, so I got the water here, the caps, and yeah. And that's that. And then the bottom flip.
Oh, look at that.
Okay.
John, that was like perfect placement right there with the camera. So pretty good ones. You should check out David's too. I don't know how I feel about David's flip. He does a little out of frame help. You should go check that one out. So anyway, but cool demonstration of I think this is actually what's getting at what's called centrifugal force, but it's that flipping motion, and when you're rotating the water, you're overcoming those gravitational forces. So again, we'll kind of play with more of this stuff as well. I had one more activity, but since we're short on time, that is what will become your homework. And that's the only thing you're going to have to do. There's no reading or anything for our next class. Just to show you, it's going to be a PhET simulation. These are these online programs. I know some students in the past have had trouble with like getting Java to work, things like that. They've been updating their site, and so this should just run in your browser. If you have trouble like getting it to work, let me know. But the link is right there in the list of announcements and tasks for today. But there's a couple things you can do. So this is what it'll look like. You'll notice there's two kind of figures here holding masses. You have mass 1 in blue, mass 2 in sort of red, and you can change the mass. It's in billions of kilograms, so this is a significant amount of gravity. So you can make them larger or smaller. They have a bunch of weird sound effects in this, but you can see that they're showing you these arrows up here is showing you the gravitational force between them, the attraction, right? And so does anyone know what N stands for? What's that unit, N?
Newtons.
Yes, it is newtons, which is, we haven't defined it or anything, but it's a unit used to measure force. And so this is looking at gravitational force. So in addition to changing the masses, you can also change the distance. You can just click and drag on them. And again, it makes a weird noise. So, so if you want, you can make some music. So you can have fun with that on your own. But there are questions you need to answer. And again, it is on our same, I was editing this earlier, but it's on the homework assignment there. It'll take you to a Canvas quiz. However, it is not a quiz that you need. It's not going to be graded as a quiz. It's just a homework assignment. But there's, I think, about 5 open free response questions that you need to answer. And that is your only homework for Tuesday. And again, the links are here. I've also posted a homework assignment, and I also posted another announcement summarizing the homework. Any questions or comments on that? The only other homework assignment is what Nadia shared earlier. Everyone should go watch Shrek the musical. Apparently, it's a hit. So, but otherwise, that is it for me today, kids. Thank you very much. Have a good day.
Thank you.
Thank you. Bye.
Thank you.
Thank you.